All right, so we're looking at some data collection for determining the internal resistance of these Energizer batteries. I have a voltmeter hooked up in parallel to my EMF source. I have an ammeter in series with an external variable resistor, which right now is disconnected, so I can get a reading of the EMF of the battery. So when there is no charge in the circuit, there's no current flowing through, I is 0, the equation V equals E minus IR. Because I is 0, it doesn't matter the internal resistance of these batteries. There's no lost volts right now. So we're reading the y-intercept, okay, the EMF, when the current is 0 or when the voltage is 3.07, the current is 0. Okay, so 3.07, even better than the 1.5 volts apiece as advertised in the Energizer company. As I connect the circuit, my variable resistor is set to sort of maximum dim, okay, so the most resistance. And you can see that I connected it now, but it's all the way dim and basically no change, right? You know, maybe this is trying to draw a little bit of, there's a little bit of lost volts there, right? So now I'm going to sort of change the variable resistor and get this in a field of view here. Here. This guy right there. Ooh. You'll see how touchy this variable is. Like all the action happens like right at the very end. Okay, so watch. As I brighten up the dimmer switch, right? See, I'm changing. I'm already basically halfway down the dimmer switch. The current hasn't changed at all. The voltage seems to be kind of doing something, but we want to get to like there's a noticeable change. And so right now I can kind of see it's at about half of a, we have to, I guess, see the scale here. So now it's the ammeter, you see it's slowly increasing. That ammeter needle is now on the very first sort of mark there above 0. And so if this line here is 10 and there's 10 lines between it, that's kind of nice. So each one is 1. And so we are literally at 1 milliamp of current. And we have 3.06 volts. So there's another data point. The first data point was 3.070, 3.06, 1 milliamp. It's important that we have milliamps as our unit, because as the data table suggests, we want to have that in amps of current. So we'll convert, milliamps to amps by dividing by 1,000. All right, and you see I'm like basically at the end of my dimmer switch. Like I started out at this end and I'm all the way over here. I got a very little sort of space left here, so it's pretty touchy. I remember in years previous, it's always fun for me to watch students sort of struggle with this. Like it just jumps all the way up to nothing. All right, so now I've increased the current all the way to 2 milliamps, and you can see that we've got a voltage of 3.05. We are losing volts, right? Like there it is. It's so theoretical, like lost volts, we're talking about lose volts. I don't see the numbers changing before our eyes, right? We're losing volts. We put a thermometer on these batteries and feel the heat energy. It's negligible. I don't notice anything. All right, let's be very careful here to adjust this. And so, go ahead, question?
3.05, was that with
2
2 milliamps?
2 milliamps, correct. And now we're up to 3, and it's still 3.05. All right, so 3 milliamps, there's basically not enough change, right? It's still 3.05. And so think about what your data is going to look like. You're going to have like, it starts at the EMF. It's going to be like this negative slope, right? But it's not going to be like a perfect trend. There's going to be points where it's like, oh, it flatlined a bit, right? Like for each of those X values, you're going to get the same Y coordinate, 3.05. So it's going to be a very, you basically have to scale your Y axis in such a way that you're spreading out this tiny change in voltage over most of the page. That's the tricky thing about the analysis of this lab, is scaling the Y axis accordingly. You want to be able to see that change, so you scale it with a tiny scale. All right, now I'm going up to 4 milliamps. I'm going up to 6. All right, we are at 6 milliamps. 3.04 is the voltage. It's like Energizer's got to be feeling pretty good about this, because it's like, hey, we advertise 3 volts even at this current, which is hardly anything. 6 milliamps, come on. But still above 3 volts, okay, 3.04. for our purposes, this is fine because we're definitely getting a change in one value as we change the other one. We'll be able to plot that. We'll be able to get a best fit line, find the slope. That's our conclusion. So, but we'd expect it to be very, very low, right? Like we're hardly losing any volts. So not a lot of internal resistance in these batteries. All right, let's see if I can jump this up all the way to 10 milliamps there. And you can see that we're on 10 milliamps, 3.03. 3.03. 10 milliamps, 3.03. We got what, 4 data points so far? We got the y-intercept, and then we had 1 milliamp, 2 milliamp, 3 milliamp, 6 milliamp, 10 milliamp. We like 7 data points. So I'm going to go all the way bright now. And look at that jump. All the way up to, now here's where the experimentalist uses their judgment to say, well, I'm looking at this perpendicular. There's no parallax there, right? Like it's like you're looking at the fuel gauge and you look from sort of like the driver's seat and you're like, oh, you're on empty, but the driver's like, oh, I got gas, but the passenger, sort of looking at a different angle. It's like, no, you're on E. That's a parallax there because they're not sort of looking at the meter perpendicular. So with my view, I can really use my judgment to say it's more than 12, but it's not quite 13. Okay, so, and that's with an analog scale where there's no like a number, like it's a discrete sort of interval, digital versus analog, right? So I can just, there's only gonna be a number here. You can see it's kind of toggling between sort of those two. And I think it actually increased a little bit. Did it drop to 3.02 when I first did it? Did anybody notice that? Maybe it is. Anyway, so the experimentalists can use their judgment and say, well, I could really say that this is 12.5 milliamps. Even though the scale isn't accurate to the half of a milliamp, I can see that the needle's in between those two values. I can say, well, it's about halfway between. And again, that's a judgment I'm making, and that's why there's some uncertainty, and that's why we use the smallest division in the scale as like the standard of how much uncertainty is there in this measurement. Well, some people might judge that to be exactly 12 or exactly 13. So there's probably plus or minus about a milliamp of uncertainty in the reading because different human beings will make different judgments about that. And anytime a human being makes a judgment, we introduce uncertainty into our results. So I guess another 3.03, unless you saw 3.02 and already wrote it down. Don't change your data to that, kind of touchy, right? So this is using the actual dimmer switch. You may recall that my other sort of strategy was to do a very inefficient one and just wire up a whole bunch of these resistors, okay? And maybe wire up like 7 of them and then take one away each time, thereby decreasing the resistance by 10 ohms, each time. And then we have sort of a little bit more, like we don't know what the resistance in this is. I could put an ohm meter up across it and, we could see that as yet another thing like, oh, as we've decreased the resistance, look how the current goes up. Right? Because it's really like we're changing the resistance in order to vary the current. Right? By changing the resistance in the external circuit, we draw more current from the battery. And you can still see that we're still above 3 volts. But we did get some good, data in terms of one quantity varied. We got some results in the other. All right. So to determine the internal resistance of a battery like this, here's what you're going to do with that data. Your ears recover. There they go. Because the terminal PD is equal to the EMF minus the lost volts, which is the current times the internal resistance, we can rewrite this as V equals negative RI plus E. And this is the equation of a line. Y equals MX plus, I like a capital B. All right. And so in order to our conclusion, we must draw a plot of the voltage measured in volts against the current measured in amps. And our data will look like, it's going to kind of look like that, I guess, because it's like two, that one's the same. But you can draw a trend line through that. Again, just scale this y-axis so that you can spread that tiny change out. Like it went from 3.07 to 3.03 or something. So you can't just go like every square is 0.1, you need every square is like 0.00 something, right? A really tiny scale to spread that change out over most of the page. That's sort of the skill I'm assessing this week in terms of your analysis. Can you rescale the axis to spread the data out over most of the page? And then find two points that intersect the gridding of your graph paper that they themselves are not data points, that you can find the slope, you know, y2 minus y1 over x2 minus x1, if you think about this as x and this is y, or, you know, like v2 minus v1 over I2 minus I1, if you think about sort of the quantities that we've measured. And then because y equals mx plus b, and we plotted v on the y-axis against current on the x-axis, m is the slope, so our conclusion, the internal resistance, will just be equal to the slope of our best fit line. And so once we've calculated the slope, that's going to be our conclusion, R, the internal resistance of the battery. R will equal the internal resistance, and it will be measured in ohms, as long as you convert your milliamps to amps when you plot them on your graph. Okay? That's the lab work for this week. So you can get to it if you want to.